Hello, my name is Gloria Casas. I'm PhD student under Dr. Stein. The presentation for today is about the effects of exogenous silanese on digestibility of dry matter, organic matter, NDF, and energy, and the concentration of digestible energy and metabolizable energy in rice co-products fed to willing pigs. I will start describing how rice co-products are obtained. The process starts with paddy rice, which is the grain as is harvested, and then the inner parts of that whole grain need to be removed. The process starts removing the hulls to get brown rice. The next step is the milling, in which the brown layer is removed to get white rice. In that process, we got rice bran. Rice bran can be full fat or defatted rice bran. The full fat needs to be stabilized to keep the quality of the product, but also can be mixed with other parts like hulls to get rice meal feed. If the full fat is defatted, we can get defatted rice bran and rice oil. On the other hand, white rice needs to be classified by size, and then grains that had less than 50% of the original size is called broken rice. The total production of rice is about 740 million tons, and 10% of this production is rice bran. So the total amount of rice bran is 74 million tons. Unbroken rice can represent 25%, that can be 185 million tons. That means that the availability of rice co-products is not a restriction to include these products in diets for pigs. However, the content of fiber, as in other cereal co-products, can limit the inclusion of this ingredient in diets for pigs. In this graph, we describe the content of NDF and ADF in rice co-products. The red bar represents brown rice, the blue bar represents broken rice, the green bar represents full-fat rice bran, and the purple bar represents the fatted rice bran. We can see that the content of NDF in brown rice and broken rice is less than 5%, but the content of NDF in rice bran and the fatted rice bran is between 20 and 25%. And also the content of ADF is greater in these two last co-products compared with brown rice and broken rice. So it's important to know the composition of this fraction in these ingredients, because that can reduce the digestibility of these ingredients, and then we can find some ways to improve the nutritional value of these ingredients. So one of the tools that we have is the inclusion of enzymes. For that reason, the objective of this experiment was to test the hypothesis that microbial silanese added to the diets may improve the apparent total tract digestibility of nutrients and gross energy and the concentration of digestible energy and metabolizable energy in these ingredients. We determine the soluble dietary fiber and insoluble dietary fiber using the monosaccharides composition by the technique described by Knudsen in 1997. For the digestibility trial, we used 80 willing pigs of 13 kilograms of body weight that were allowed in a randomized complete block design to 10 diets, 2 blocks, and 8 replicates. We had one basal diet and 4 diets with each of 4 rice co-products. Here we have the description of experimental diets. Each diet contained corn, soybean meal, and the ratio between these two ingredients were similar in all the diets. And the rice co-products were included at 50%. We also have 5 additional diets containing 16,000 units of microbial silanese. All diets also contain 1,500 units of phytes. The data were analyzed using mixed procedure of SAS, like a 4 by 2 factorial, 4 ingredients, and 2 level of silence, and the fixed effects were the rice coproduct, the silence, and their interaction. Now we have the results and discussion. First, we will see the results about the fiber composition, and in this graph, we keep the same color that I described previously. In the x-axis, we have the fraction of fiber, and in the y-axis, we have the percentage of fraction of fiber. We can see that the content of soluble dietary fiber was less than 5% in all rice coproducts, but the concentration of insoluble dietary fiber was less than 5% in brown rice and broken rice, but more than 20% in full fat rice bran and defatted rice bran. From this fraction of insoluble dietary fiber, cellulose represent between 5 and 7% in full fat rice bran and defatted rice bran, and was 5% of lignin. Now, in this graph, we have the composition of insoluble dietary fiber in these rice coproducts, and we can see that the most predominant monosaccharides in this fraction were arabinose and xylose in full-fat rice bran and defatted rice bran. That means that the main polysaccharide in this fraction was arabinoxylans. The concentration of other polysaccharides like glucans is very low. Checking the ratio of arabinose and xylose, we can see that the ratio in brown rice and broken rice is greater compared with the ratio in full fat rice bran and the fatted rice bran. That means that the substitution of arabinose in the backbone of xylose is less in these two ingredients. Now, these are the results for digestibility. So the digestibility of dry matter, organic matter, and digestibility of gross energy were not different when silence was added to the diet. However, in this graph, we have the concentration of digestible energy. In the x-axis, we have the rice coproducts, and in the y-axis, we have the concentration of energy in kilocalories per kilogram. The orange bar represents the values of digestible energy when silence was not added to the diet, and the blue bar represents the values of energy when silence was added to the diet. The content of energy in brown rice and broken rice when silence was not added to the diet were 4,000 kilocalories, and they were not different. The content of digestible energy in full fat rice bran was 3,700 kilocalories, and the content of digestible energy in the fatted rice bran was around 3,000 kilocalories. But when silence was added to the diet, the content of digestible energy was the same in brown rice and broken rice, but increased in full fat rice bran. In this graph, we can see the content of metabolizable energy, and we observe the similar pattern, but in this case, the content of metabolizable energy increased also in the fatted rice bran when silence was added to the diet. The low concentration of xylose and arabinose in broken rice and brown rice indicate less concentration of arabinose silence and explain the low activity of silence in these ingredients. Also, the high concentration of arabinoxylans in full-fat rice bran and defatted rice bran may explain the increased values of digestible energy and metabolizable energy when silence was added to the diet. And the low arabinose and xylose ratio in full-fat rice bran and defatted rice bran indicates less substitution of arabinose, and that can help to increase the digestibility of energy in these rice coproducts. In conclusion, we can say that broken rice and brown rice have greater concentration of digestible energy and metabolizable energy than full-fat rice bran and defatted rice bran. And also, microbial silanase may increase the concentration of digestible energy and metabolizable energy in full fat rice bran and fat rice bran. The implication of this research is that the high content of digestible energy and metabolizable energy in full fat rice bran indicate that these ingredients can be included in diets for weaning pigs. Also, this research indicates that microbial silence can be beneficial in diets containing full fat rice bran and fatted rice bran. So thank you for your attention, and if you need more information, you can visit our website.